Now, in the previous section, section 5.1, we looked at OpAmp terminals, right? In the next section, section 5.2, we are going to take a closer look at the OpAmp terminals and then develop this a little bit more. Now, this is what we did in the last section. We saw operational amplifier terminals. It's a 3-terminal device, remember. There is a VN, there is a VP, and then V output. V output is A times VP minus VN. In this section, what we are going to do is to simply look at the 3 terminals again a little bit closely. So here is the same operational amplifier with its VN terminal and VP terminal. What we are going to do is to pick some numbers. Okay, remember V output is A times VP minus Vn, right? So let's see what happens when we plug in some numbers. Okay, the first thing I'm going to do is to I don't know, pick a value for A. Okay, let's say the value of A is a typical value for A is a large number, 10 to the 4, 10 kilo. Okay, 10 kilo. Let's say volts per volts are the units. It technically does not have any units. The open loop gain, voltage gain, does not have any units, but we still show it as volts per volts. Let's pick a value for plus VCC. I don't know, the typical value is 10 volts. Okay, and a value for the negative power supply, that's going to be negative 10 volts. Okay, everybody with me? We're just randomly picking some numbers to understand this operational amplifier a little bit more. Okay, now let's see. I'm going to clear this up a little bit. Okay, and then I'm going to make everything black. That way we can color code now. Okay, so let's start by picking a value for VP equals to 0.1 or 0.9 millivolts. Okay, and let's pick a value for Vn. That makes it, let's just pick a value for Vn to be 0.7 millivolts. Okay, now we should be able to calculate V out. Okay, V out is going to be, let's do this. Let's write all of this in red. Okay, so let's write all of that in red. V output is going to be A, which is 10 to the 4, multiplied by Vp 0.9 milli minus 0.7 millivolts. So that's going to be 10 to the 4 times 0.2 millivolts. So you multiply that, you get a value of V output equals to 2 volts. Simple, right? So let's plug in a different value. We are just throwing numbers as we please, right? So let's pick a value for Vp. Okay, let's pick a value for Vp equals to 0.5 millivolts, right? And then Vn value equals to 1 millivolt. Okay, what would be your output in this case? Your V output would be remember they're color coded. V output would be your A, which is 10 to the 4, okay, 10 to the 4 multiplied by Vp minus Vn, right? So that's going to come out to be V output is going to be 10 to the 4 times negative 0.5, so it's going to be negative 5 volts. Straightforward, right? So let's pick another number. This is going to be a bit of an interesting scenario, okay? Because I'm going to pick a value that might throw the op-amp out of its linear region. Let me show you what I mean. Let's pick a value for Vp equals to 3 millivolts, okay? And let's pick a value for Vn to be 1 or let's 0.5 millivolts, right? We are picking values for Vp and Vn. Now, if we are to calculate V out in this scenario, okay, V output equals 10 to the 4 times Vp minus Vn, okay? So that's going to come out to be around or 10 to the 4 times 2.5, 25 volts, okay? Now, this is a problem, okay? 25 volts. The op-amp simply cannot put out 25 volts. Why? Because the power supply, the maximum power supply that we are providing to the op-amp, that's 10 volts, okay? The op-amp cannot drive an output that's larger than 10 volts. So in this case, the output is really going to be 10 volts, okay? Similarly, let's pick another number. Let's pick a Vp value equals to 1 millivolt, Vn value 5 millivolts, okay? The same value for A. Now you see V output is going to be A times Vp minus Vn. That's going to be 10 to the 4 times Vp is 1 milli minus 5 millivolts is your Vn. So you would expect your output to be negative 40 volts. Clearly, the op-amp cannot produce this output. Why? Because the minimum power supply that we are doing is negative 10 volts, okay? So there seems to be a limit to how far, how high or how low the op-amp can drive, okay? So the op-amp, the operational amplifier, has limits on the output voltage, okay? V output voltage, we saw that the V output voltage is A times Vp minus Vn, okay? If the output is between plus or minus VCC, okay? But if this factor, okay, if this particular factor goes over plus VCC, then the output is going to saturate at plus VCC, okay? I'm going to show this to you in a formal manner. Similarly, the minimum voltage that can be supplied is by the op amp is negative VCC. So this guy A Vp minus Vn, when this term is less than negative VCC, okay, we have an op amp, okay, we have an op amp that is saturating, okay, this is called saturation region. Now, if this term is greater than, okay, if this particular term is greater than plus VCC, okay, then your op amp is again going to saturate as well. Okay, so both of these regions are called saturation regions. There's no rocket science to this. Just pay attention. The maximum value of the output is plus VCC. The minimum value of the output is minus VCC. That's all this equation is saying. Okay, all that this equation is saying is that the V output minimum of an op amp is negative VCC and the V output maximum of this op amp is positive VCC. That's all there is to it. So when you see your op amp output going above VCC or below VCC, then you know that the output is going to saturate. It's going to remain constant at the power supply voltages. Okay, just like this example. Okay, in this example, the formula tells you that the output is really expected to be 25 volts, but then the output really peaks off, levels off at the positive power supply. Okay, so we are going to look at this. They are called saturation regions. We are actually going to look at this using a graph in the next video.